which turns the top upwards. You need to go through that slowly, sort of in the bath or somewhere where you can sort of relax. But it's exactly the same. Now that is why a whipping top like this has a round bottom, because what happens, and it's quite spectacular when you actually are seeing this, you get it going, you give it a whip and it falls right over, it's almost at that angle, and it rights itself quite easily, so it keeps going. So a round bottom top will right itself, okay? Now if that's not enough, let's go on to the next slide, and we come to the tippy tops. Now you all should have at least a few tippy tops. I've got, I can't resist them if I see them in a shop. I've got a little one. It's a little, that works fantastically. Middle size, and I've even got a giant one, which will work great upstairs. But if you've not seen these, spin it, and it turns itself upside down. Some people haven't seen those. I mean, there's hundreds around. If you look, any wood shop will have some of these. And this works in the same way, but there's so much physics in this. There's so much physics in this. Let me just need to finish, but it's spinning like that, okay? Spinning around, it can perhaps go on to the next. It then turns upside down. That means relative to the top, it must have changed its direction, because if it's spinning clockwise from above, when it's like that, and clockwise from above when it's like that, it's got to do that because of conservation of angular momentum. It's changed it, so it must have stopped. So halfway through, the top stops spinning on its axis and starts spinning around bodily. So that's one little point you could make. I mean, you get your head around all these. Next, if it's spinning like that, and it's spinning then upside down like that, you've raised the centre of mass. So you've lost energy. Therefore, you've lost angular momentum, because it's not spinning as fast when it's upside down. How can you lose angular momentum? Answer, you must have a couple acting. And it's the frictional couple of the bottom of the top. Does that make sense? It's got to get the bottoms in your tops right. So go on to the next slide. No, well, yeah. So the top is spinning in the same way. You can do the same thing with your fingers, and you produce the couple that will actually turn the top against its, so it goes upside down, because these are designed with the centre of mass not on the left but on the right. So the couple produced turns the top in the opposite direction. But even cleverer than that, it's got to stand on its head, because once it stops and then it starts spinning again, and then the bottom hits the surface. Now it's a small rounded bottom, so it turns itself upright. Isn't that amazing? I mean, you could go on forever. No wonder Pauli and Niels Bohr were fascinated by it. And it's sort of been, in lots of papers, it's been mysterious that for years and years. And I think, I've been thinking about it for a year, and I think that's just about cystic. Very quickly, we'll just go on to the last, there's my hand. You can just say it's simply that large bottom tops turn upside down, small radius of curvature, self-erect. That'll do for your explanation. Right, very quickly, keep going. There's a nice NASA site of them spinning tops in space, where you don't have the gravity. You can do tippy tops with cream eggs and spin a cream egg horizontally. The small ones work much better than large ones. I think they change the shape slightly, but you can still get a large one to turn on its edge. Rattlebacks are not really tops, but they do come in the category because they'll only spin one way. So that spins that way. You can say stop and it stops. Okay? Or I can say stop but it doesn't stop. But that one I've turned upside down. Stop. And if you sort of measure your timing correctly, it looks Stop. That one's not. Stop. Or the other way, if I spin it the other way, it doesn't happen. So you tell somebody, you tell it to stop. And people do. I had a first class honours from York University who was convinced this was the Coriolis force or something. You know, but that's just the imbalance, it's not symmetrical. So it does that. These are originally some sort of aboriginal stone that was a magic stone. Of course, it's not magic, it's science. Okay? An oilless disc which spins beautifully and makes lovely noises as it goes down. Angular momentum is concerned, it gets faster and faster. Even Homer was actually fascinated by one. So there is something. It makes a lovely noise. Just you can look at this upstairs and work out how it does what it does. It's just what happens to pennies, you know, when you spin. When you spin a penny, that's what happens. But we're just exaggerating things. And it's pretty with the lights in here as well. So there we are. Thank you for listening. What I'll do is we are going to do some work now, some real work, and I'll put some of these on a table upstairs, so when you come for your coffee, you can have a go and ask us anything at all. I hope that's given you some ideas, maybe just one or two. You might think, yeah, I'll go and have a try with that. And an oilless still. There's an oilless, Euler, Euler or Euler. There's an oilless just society you can join. So, you know, but I mean, there's tippy top society, I guess.
Right, well, we're going to go. Thank you very much, David. We're going to go down to the Clyde room now, but the coffee and the wine is actually out there. So if you want to nab something on your way down, and we've got some members of the QDT team downstairs. And then after that, Drew's going to tell us a wee bit about some of the resources on our Pixies website. So the coffee and the wine is there if you want to help yourself, and then go downstairs.